Okay, so let's start. Last 10 minutes we'll discuss about the quiz, tomorrow's quiz paper, and we'll continue our journey of digital design. Okay, so we have seen certain combinational circuits already. Can you tell me what are those combination circuits we have seen? Of course, half adder, full adder, and 4-bit binary parallel adder, subtractor, and subtractor come adder, all those things we have studied, right? And BCD adder also we have seen. We have seen what is BCD addition also. Hope all of you are thorough with these topics, right? Don't prepare just for the quiz. See that you are going to have midsem also. Now tomorrow never comes. Just start preparation, okay? So we will continue the journey of same combinational circuits, right? There are a lot of combination circuits available which are part of your processing system, right? Your entire processing system, which you call it as a microprocessors or microcontrollers, has all these things internally built. So we are going to study the basic building blocks in digital design. Let us see. Comparator. What is comparator? What is comparison? You all know, because every day we try to compare ourselves with others. It is comparison has become quite familiar, attached to our culture, right? Okay, so comparison, what it does, it says whether one is equal to other, one is greater than other, one is less than other. In this case it is going to be bits, right? Single bit. Okay, so when you compare single bit, it is called as one bit comparator. Okay, and when you compare 2 bit, it is 2 bit comparator. When you compare 3 bits, it is 3 bits comparator. Okay, comparator is quite easy, right? So next you are going to study about decoder, right? 2 to 4 line decoder, 4 to 16 line decoder, 4 to 16 using 3s to 8 decoders. So this decoder is nothing but it will decodes the code and give certain outputs. See, in a simple way, I want to tell you what is decoder. It's very simple. Anybody can understand this. What is decoder? Okay, we are going to deal with that. Don't worry. See, comparator, you know, right? No doubt about it. If I ask you to compare, okay, 0, 1, this is A, this is B. Comparator means A equal to B, okay, A less than B, okay, A greater than B. Okay, so you're going to have three things. Suppose your A is 0, B is 1, okay, can you tell me, is it A equal to B? No, so it will give you 0, false. A less than B, is it A less than B? Yes, it is A less than B, 1. Is your A greater than B? No, so what will you get here? 0. Similarly, if you take 1 0 combination, can it be equal to B? No. Is it A less than B? No. Definitely it is A greater than B. So it is going to be 1. Suppose if you have, say, take 0 0, you get 1 here, right? You get 0 here, 0 here. Yes or no? Hope all of you are able to catch this. It's something very easy. You can remember just by concentrating on what I am telling you. Just be with me. Now, what about 1 1? Come on. It is 1 and 0 0 here. That's all. This is comparator. How can you extend it to 2 bits? 0 0 0 1. Right? So that's all. You just have to compare this. Right? Now, assume that it is 2 bit. Your A is 2 bit, B is 2 bit. Okay? I will give you some random numbers. I'll take some very random numbers. Okay, can you tell me, can you fill this? Whether A is equal to B? 0. Whether A less than B? Yes. Whether A greater than B? No. This one? 0, 0, 1. Of course, this is 1, 0, 0. This one? 0, 1, 0. This is what comparator is. Have you understood now? Okay. Now, what is decoder? Have you understood this? Right? What is decoder? It's very simple. It decodes. You have some code with you and it decodes. Decoding means what? You got some outcome out of that. Right? See here. Decoder is very simple. Listen carefully. Suppose this is your decoder, okay? I'm just writing it as a black box. Let us see what is there inside. It is going to be a logic circuit. It's going to be a logic circuit. There are some combinations of gates over there. We are going to see that in detail. Don't worry. Assume that it has got 2 inputs and 4 outputs. Assume that it is 2 inputs and 4 outputs. I will write this input as A and B. Okay, I will write this input as A and B. I will write the output as O0, O1, O2 and O3. O0, O1, O2 and O3. Okay. Now, what this decoder does? Of course, when you have your input as 2 inputs, 2-bit input, this is supposed to be 2-bit input. Output is going to be 4-bit output. There are 4 bits, there are 4 outputs. Okay, 4 outputs here. Okay. Now, of course, as usual, when you have 2 inputs, how many combinations will be there? There will be 4 combinations. Okay. Now, how many outputs? O0, O1, O2, O3. Okay. Now, this decoder is something. Okay. It does specific task of decoding. What it does? Whenever A and B are 0, 0, this O0 will become 1 and all other outputs will become 0. Okay. Whenever AB is 0, 1, your O1 will become 1, all the outputs will become 0. Listen carefully. Right? See, whenever A and B is 1, 0, okay. Now what will happen? This O2 will become 1, all other outputs will become 0. When it is 1, 1, O0, O1, O2 will become 0, this will become 1. This is what called as decoder. Right? See, suppose if you connect an LED here, assume that you connected an LED here, okay? Or assume that you connected a locker, right? Locker 1. And this you connected to locker 2. This is connected to locker 3. This is an LED, locker 3. This is connected to locker 4. Assume that there are 4 lockers connected. Now you are going to give code through A and B as a AB. So when you give 0, 0 as a code, this particular circuit will decode it and it will open your locker 1. Right? When you give 0, some other combinations other than 0, 0, does locker 1 will open? No. So when you give 0, 1, assume that this LED will glow whenever you have a signal 1 here. Listen carefully. I have already told you during our first class, right? LED and the switch, right? Now you see here this LED will glow only when you pass 1 to this. When you pass 0 to this LED will not glow. Have you understood this? That means when your input combinations A and B are 0, 0, this will become 1 okay, and this will become 1. What's happening? Okay, here. This will become 1, this will become 0, 0. That means this LED will glow, right? And this locker will open. Now suppose if your combination is 1, 1, if your combination is 1, 1, this is 0, 0, 0, this is 1. So this LED will glow. So this circuit decodes your input, This is called decoder. And always see that your decoder input output relations will be always to the power of 2. When the input is 2, what is the output? 4. When the input is 3, 2 to the power of 3, 8 output. When the input is 4, you will have 16 outputs. Right? 16 combinations can be taken from the output. Sorry, 16 outputs can be taken from 4 combination input. So have you understood about this decoder action? This is what called as decoder. Right? It decodes. Suppose your code is 0, 0, give the input to this, it decodes such a way that O0 will open, 0, 1, O1 will be 1. Now, question, there is one more variation for this. Listen carefully. There's one more variation for this. This type of output where your input is 0, 0 and this output will become 1 and all will become 0 is called as active high inputs. It's called as active high outputs. Listen carefully this jargon, active high outputs. Why it is called active high outputs? Active high because all input combination will make the output to be 1. That particular line output will become 1. Other line will become 0. This is called active high. Now what is active low? Active low is reverse of that. In active low, what will happen? In active low, listen carefully. If your input combination is 0, 0, listen, your input combination is 0, 0, this will become 0, listen carefully, and all this will become 1, 1, complement of that. Right? This line will become 0 and all line will become 1, 1. Now can you tell me, what about the combination 0, 1? Come on. This will become 0, this will become 1, 1, complement of that, active low. Now for 1, 0, this will become 0, all this will become 1. For 1, 1, this will become 0, this will become 1, 1. This is the difference between active low and active high. And always active low output will be written by having a bubble here. Suppose you have a decoder, listen carefully, you have a decoder, 2 inputs and 4 outputs. And if there is a bubble here, that means it is active, come on, active low. That means whenever your input is 0, 0, this will become 0, all other output will become 1. Or whenever your input is 1, 0, this will become 0, all outputs will become 1. This is called a decoder with active low output. Right? If there is no bubble here, then it is active high outputs. Have you understood this? Okay, that is the difference between active low and active high decoders. Okay, now let us go little bit detail. You have this, see, you have in between here something called 3 to 8 decoder, 4 to 16 decoder. Now similarly, it is possible to assume that whenever you want to design 4 to 16 decoders are not available. Assume that 4 to 16 decoders are not available. Do you stop your work? No. You can construct 4 to 16 decoder using 3 to 8 decoder. So in that case, you have to use 2 numbers of 3 to 8 decoders and construct 4 to 16 decoders. Of course, output is power of 2, right? Always output is power of 2 in decoder. Remember this. If input is 4, this is 2 to the power of 4. Input is 2, 2 to the power of 2. Input is 3, 2 to the power of 3. So like that it continues. Suppose you don't have 4 to 16 decoder IC available with you, chip available with you, you can use 3 to 8 decoders and construct 4 to 16 decoders. Same function, same function. Have you understood this? Okay. Now let us see how do we design this. Question is, design a combinational circuit which has 3-bit input and output is its square. Of course, these are the outputs, you know that. Okay, this is a simple combinational circuit which has a relation between input output as a square. Okay, this is not a part of decoder, but this is combinational circuit. Okay, now see the question. You have to design a combinational circuit. What is combinational circuit? You know, it's just a element of your AND gates, OR gates, or something like that. And what it should do, input is going to be 3-bit input, and output is going to be square of that. Okay, of course, when you just square that, a 3-bit number, your number of bits may go long, right? Yes or no? So your output will be that much length of bits. Suppose if you take, say, square of 3. What is square of 3? 9. 9 means, of course, okay, your output. Suppose if you take a square of 7, what is the 49? 49 can be represented with how many bits? You need minimum 6 bits, right? Yes or no? So you can represent that much number of outputs. The number of bits for output is going to be 6. Yes or no? Have you understood why I have here x0 to x6, x1 to x6, right? So I'm going to develop a combinational circuit, okay, which can give me a square of a 3-bit number. A square of a 3-bit number, okay, if you take 49, okay, this is 111, 49 in binary, right? So it takes how many bits? 6 bits. So we need maximum number of 6 bits. 6 bits means 6 outputs, yes or no? 6 bits has to be there. Okay. So now let us draw a circuit for this. Okay, I will just draw a simple black box. How many inputs will be there? How many outputs? 1, 2, 3, 4, 5, 6. Okay, so your least significant bit, I will just try to put it here, x1, x2, x3, and this is going to be your MSB. This is your MSB, this is your LSB. What is there here? You will have to do. It's very easy. You have to find out an equation for x1, find out an equation for x2, find out an equation for x3, find out each and every variable equation. Right, from where you get the equation? See here, A, B, C, these are the outputs. What is the square of 0? 0 only, right? What is the square of 1? It is 1 only, right? What is the square of 2? 0, 0, 0, 0, 1, 0, 0. Yes or no? 4, right? This is 4, na? Okay. What is the square of 3? See, 0, 0, 1, 0, 0, 1. What is this? Binary equivalent of 9. 1, 0, 0. What is this? Binary equivalent of? Come on, I want answer to come from you. 1, 0, 1. What is this? Binary equivalent of 25. 1, 1, 0. What is this? Binary equivalent of? Come on, 6. Binary equivalent of? Enough, because it will be, if you go for 4-bit, you will have still more inputs and outputs. For doing it by hand, this is enough. Okay. Now, tell me, how do you get the equation for x1 now? Can you get the equation for x1? Can you get the equation for x1? Sorry, x6, x1. Put it in a Karnaugh map. Come on. Put it in a Karnaugh map, 3-variable Karnaugh map. Come on. Get me the equation for x1. I want to see how many of you are doing it. I told you tomorrow's quiz, the 3-variable Karnaugh map is there, right? I'll put A bar, B bar, C bar, B bar C, BC, BC bar. 0, 1, 2, 3, 4, 5, 6, 7. Tell me, where and all I should put 1? 0, 0, 1. Here I should put 1. Then 0, 1, 1. Here I should put 1. Right? Then, sorry, this is A bar, this is A. Okay? This is A bar. Okay. Then, where and all I have 1? 1, 0, 1. Here. Right. 5 and 7. Okay, what is the output now? Tell me. You just combine this. Just combine this. These two will go anyway. So what is the common between this and this one? C. So answer will be C. Anyone in this class, I want to know at this point, doesn't know how to do this. You are in a danger zone. You are in a danger zone. Right? Please, still you have time. You can meet me anytime. I will teach you this. This is very important. Or else you can ask some of your classmates. Don't be shy. Right? Don't feel that somebody may say you are dumb. No, everybody is dumb in this world, right? You have to learn this. Have you understood this? Okay. Now, can you get the equation for x2? Okay, when the outputs are like this, can you tell me what is the equation for x2? x2 will be always 0. Okay, can you get the equation for x3? Use K-map. Use K-map. Get the equation for x3. Do it. See, this is the practice for you. Why can't you do it? Can you get the equation for x3? Put it in a Karnaugh map. I will not just keep on doing this in every class. Can you get the equation for x3? Do it yourself. Equation for x3 is going to be BC bar. Can you get the equation for x4? Everywhere you try to put Karnaugh map. Everywhere. How many Karnaugh maps are required for here? How many Karnaugh maps are required? Practically 6. Right? But x2, since it shows everything 0, you can just make your x2 is equal to 0. Suppose if x2 shows everything 1, suppose if there is everything 1 here, can you tell me what will be x2? x2 is equal to 1, come on my dears. That's all. Okay. Now, see, once you get this Boolean equations for everything, can you tell me what will be the next? What will be the next one? Come on. What will be next? Once you get this Boolean equation, come on, I'm asking you this question. What will be next work? Of course, implement it. Once you bring tea powder, coffee, everything at your home, what is next? Tell me. You make tea, prepare tea. That's all. So everything is ready now. Now you implement it using basic gates. Basic gates. Come on, next. If the question says implement it using only NAND gates, what you will do? First you implement it in basic gates, then try to convert each and every basic gates into required gates. You all know about it. This is very important, it's very much required for the quiz. Fine, unless you practice just by reading, looking at the notes at your phone is not going to work out. You have to do something. So have you understood this now? This is a combinational circuit. You are developing a hardware for getting the square of a 3-bit number. Of course, this if you just put this in a logic circuit, input will be your plain binary number, output will be a binary number, which is going to be your, come on, which is going to be your square number. Yes or no? Square number. Have you understood this? Okay. This is the way you can create a combinational circuit. Now see, there is another question. See, you may get this type of question in your midsem examination. Design a combinational circuit to do so and so. One question we have already done. Can you read the second question? Second question says, ABCD is a BCD number. Design a circuit whose output is 1 when A is equal to 0, B is equal to 0, and C is equal to 1, or when A is equal to 0 and B is equal to 1. Listen carefully, listen carefully. This is a condition here. You have to write your truth table in such a way it will satisfy these conditions. For this type of question, you have to write the truth table first, which satisfies this condition. See, it says input is ABCD. That means definitely there are how many variables? 4 variables. Right. Now what is the output? Listen carefully. Your input is A, B, C, D. Okay. Now how many combinations are there for you? There are 16 combinations are there. Okay. And you have one output F. One output F. And this F output is going to be 1 when A is equal to 0, comma B is equal to 0, and C is equal to 1. It's compulsory. And C is equal to 1. Or when A is equal to 0 and B is equal to 1. Can you tell me where and all you can put 1 in this case? See, A is equal to 0, B is equal to 0, right? See here. And see here, C is equal to 1. That satisfies, right? It is OR condition. See, this, I'll just take this as X, Y. Okay. So you get when X or Y, your F is equal to 1. This or this. That means when A is equal to 0, B is equal to 0, okay, and C equal to 1, moment you have that 3 combination, okay, definitely output is 1, yes or no? Which says that it is OR condition, this or this. Okay, now of course, where and all that condition satisfies? A is equal to 0, B is equal to 0, C equal to 1. Where and all? Tell me. This one. Next one also, of course. Right. That's all right. Okay. What about other conditions? A is equal to 0, B equal to 1. See, A is equal to 0, B equal to 1. All this will become 1, right? Yes or no? Because this or this. Is there any other condition which satisfies this? No. You can put all other combinations as don't cares. We don't need that, right? We can put it as a don't care. Right? Okay. Now can you get a circuit for that? See, all these are one. You can put XXX in this case. No problem. You can put XXX in these other places. See, those inputs, other remaining inputs are not required at all. It is immaterial for us. Have you understood this? Remaining combinations which are not going to satisfy that, it is not required for us. See, for example, 1 1, AB 1 1 and CD 0 0. So those combinations are actually not considered because those are not required at all for us. So only for these inputs, your output should be equal to 1. That's why we are going to use this. Huh. If you can put 0 0 over there, you can put XX over there, no problem. Yeah, see here it says that A is equal to 0. These conditions, we are not going to, no, 0 0 0 0 0 0 0 1. We are not going to use it at all. See, we have this A is equal to 0, B equal to 1. We are not given A is equal to 1, B is equal to 0 here.
So in those empty spaces, should we put 0 or X?
X you put.
So if we put X, then the whole grid will become 1.
No. See the condition here. See the condition here. 0 1, okay, 0 0 0 0. A B 0. See, A and B are 0. See, it should satisfy this condition also. Just check other conditions are getting satisfied. Just check this. A is equal to 1. Of course, true. Yes, you are right. It's written BCD number. Very good. For BCD number, anything after 9 will be going to be your don't cares. Very good. It is BCD number. Your number above 9 is going to be don't cares. That means those numbers are not used in the input at all. That's why you put all X in this. Good. Yes. When it is said that input is a BCD number, your input is only between 0 to 9. I've understood this. Your all input combinations above 9, it is immaterial. It is don't care. That's why whether the output is 0 1, because of that we don't consider it all. That's why you put all X in everywhere, the number above 9. Right? Check this. This is very important. BCD is written that it is a BCD number. It's a BCD number. Remaining places, can you just solve this? Can you solve this? So you get one equation for F is equal to B plus C. F is equal to B plus C. Okay? This type of question you have to practice for your midsem examination. Why I am telling you, there are various combinations of questions can be formed for various conditions like this. This you have to understand very well. Okay? First you have to see how many variables are there. Then you see whether number is BCD or if the number is say binary, right? Suppose if I say it is not BCD, what will be the case? Tell me. In place of X, what will be there? 0. In place of X, all will be 0. All will be. No, see, in this case, listen carefully. In this case, since it is BCD, all the combinations above 9, we are making it as a don't care. Why? Because those inputs are of not importance for us. Whether your output will be 0 or 1 because of those inputs, we are not bothered at all. That's why you put all this output to be equal to X. Suppose if I say this is not BCD but it is binary, then what I should put in this place of X? 0. 0. That means other than this, for this input combination, output will be 0. But same time you check once again, you going to satisfy this. For above 9, are you going to satisfy this? This condition, it has to, if the condition is satisfied, output will not be 0. Right, now check for above 9, are you going to satisfy that A is equal to 0, B is equal to 0 and C is equal to 1, or A is equal to 0, B equal to 1? Are you going to satisfy this? No, right? Nowhere it is going to satisfy. So all these are going to be now 0, 0, 0, 0, 0, 0, 0, 0. Can you tell me what is going to be your equation? Suppose if it is a binary number. Suppose if it is a binary number, output will be equal to, see, you can do combination of this, okay? Combination of this, you can do combination of this. That means F is equal to A bar B plus combine all these 4. What is common between these two? A bar C. You can bring A bar outside. This will be B plus C. And this is the case if the input is binary. Have you understood this now? Right? So you can design any type of combinational circuits where your input is given in the form of a behavior. Where input is given in the form of a behavior. Is it not a behavior is given here for you? Have you been given a truth table? Try to understand this. If you have been given a truth table, drawing a circuit is very easy, right? Right, you just put it in a K-map and then solve equation. Suppose if the behavior is given, right? Assume that you have been given one paragraph of some logical reasoning, right? Right, a lot of examples like that, okay? Which is very useful for you to write a program. We'll do some questions on that, okay? You must be able to develop a combinational circuit for this. Have you understood this? Okay. Now let us see one more topic. I said comparator. Comparator, okay? It can be a single bit comparator, it can be 2-bit comparator, 3-bit comparator, it can be n bit in general comparator, right? So how many outputs are there from your comparator? 3 outputs. Equal, not equal, equal, greater, less than, right? Now this slide is self understandable, right? You have 2 inputs. This is 2-bit comparator, single bit comparator, single bit comparator. Single bit comparator means definitely input will be 2, yes or no? Always you compare between 2 bits, right? Input will be 2, output will be 3, right? Now how to get a combinational circuit for this? Get a equation for this, get a Boolean equation for this, get a Boolean equation for this. You get equation for this will be PQ bar, equation for this will be PQ bar plus PQ, equation for this will be P bar Q. Can you draw the circuit for this? All of you understood how we got this equations? Simple K-map. One equation, second equation, third equation. So you get 3 equations, you get 3 K-maps, and you get the equations and try to implement it using combinational circuit. This is where you're going to implement. Okay. And we are going to give a slide, don't worry. Right? Can you implement this? If you implement this, this is going to be your circuit. Right? Okay. So can you do this?